the total number of points that I'm going to generate. So approximately these many points should be coming from that particular class. And this is not exactly right. What would have been the exact way of generating this? For every data point, I should have generated it from a multinomial distribution with this probability. That would have told me whether the class is 1, 2, or 3. But because n is reasonably large, I am approximating as if the number of data points are pi times n. Otherwise, I should have been in exact the way to generate this quantity. It should have been basically looking at every one of them. I should have generated a multinomial distribution. I'm going to play around with this later. Now, so actually, let's put this as 2 for now. So although the data came from 3 classes, the number of, I don't know actually the number of classes truly in the data, so I could guess it to be something else, run it, and then figure out, and then later on I will ask what happens, how do we get what is the right number of classes. Pi's is randomly the number of classes. I just randomly generate some numbers and then renormalize to get the pi's. Mu's have been randomly generated, sigmas have been randomly generated. It's just that they're all set to be equal to identity, and then we'll rescale to see what is going to happen. So let's run this and see what kind of data ends up getting created. Over here, and you look at pi's. So because I had said 2 classes, so it's generated 2 numbers, which is approximately what we have. The mu is what it generated. The first, Python loves everything in rows. So that is the mean corresponding to the first class. This is the means corresponding to the second class. Not in columns, but in rows, right? Let's look at what is the data that I've generated. This is huge, so let me just so this is the first data point that has been generated. It's a 2-dimensional quantity, and there are 1,000 of those. So 1,000, that is the last data point that has been generated. Okay. So let's go back to the function. What is happening over here? If I take the shape of that matrix that I've generated, the number of rows is equal to the number of data points, and the number of columns is equal to the total dimension of the problem. So in this particular function, P will refer to the dimension of the problem. In this particular case, it's going to be 2. N will refer to the total number of data points that are there. So there's going to be 1,000 of them. How do we know how many classes are we working with? I'm just going to look at the length of the pi's. The pi's have been sent into this function. The length of the pi's tells me what is the number of classes that's going to be there. We set that to be equal to 2, and the k will be equal to 2. And now what I'm doing is basically computing the log likelihoods. Why do I need this XA, XB business? I don't remember now. We can get rid of these. I don't know why I keep track of that. I think I was trying to copy it from somewhere else. Yeah, okay. Okay. So now what I'm doing is constructing an E step. So this is another interesting way of looking at things. So WS are the weights on the various data points. It's going to be K times N. So K is the number of classes, N is the number of data points. So what this is going to try to do is it will say for each particular data point, what is the weight on the various classes. Alright. So K is the class, N is the data point. For every data point, I want to compute what is the probability that it will contribute to a particular class. How do I do this? Part of this is Python tricks, which are actually also important to know. Remember the zip function? So the zip function anyway is going to give me pi1, mu1, sigma1, pi2, mu2, sigma2. That is what the zip is. Enumerate, what it does is that it adds a 0 in front of me. Okay, so 0, pi1, 0, pi0, mu0, sigma0. 1, pi1, mu1, sigma1. So this, what is the length of this zip list? This is exactly equal to the number of classes that I have. Right? For the total number in this zip is the number of classes that I have. I'm numbering the classes from 0 to k minus 1. So this j will basically be number of the class. Pi mu sigma belongs to this zip. For that particular case, you look at the old value of pi, old value of mu, the old value of sigma, and you evaluate at all possible values of x. This is now a row of this matrix. For the jth class, what you do is you take the old value of pi, the old value of mu and sigma corresponding to this particular class j, and how do I know that that's the correct one? Because I've enumerated these, and you evaluate at all possible x's. What this does is that for all possible values of x, it just normalizes everything. This is simply a weight. I need to renormalize that to get the probability of the different classes. That's what that does. Right? What happens over here? This actually is a very interesting summation. How many of you have seen Einsum? For those who, this is a subset of people who have done Python. Einsum, have you come across this? No. Okay. So this stands for something called Einstein Summation. Einstein Summation was this convention used in physics, which says that anytime you have the same index repeated, you sum over it. So Einstein did not generate this summation exercise. This was some mathematicians who had come up with before, and when he was doing special and general relativity, he had to add over many things. So the convention being used is that anytime two components are the same, you add it. So let's look at this WS, which will give you some idea so WS is a matrix. So right now, WSJK is the probability, is the weight that Y, let's call it I for the moment, Yi is equal to J given Xi and theta. This is what the matrix WSJI is right now. After this computation, what it's found is what is the probability that on the data point I, the class is J. And what we want to do is, in order to figure out what the pi is, so pi j will turn out to be the summation over WSJI, I going from 1 through n, divided by n. This is the probability of seeing the class J. Okay? So what that Einstein summation, where did it go? Over here tells you is that sum over, so the WS matrix looks like, how did I do it? K times n. So this one says that you just add up on those, this k n dimensional, you keep the k the same, and in the middle, which is the n, you just add them up over all n data points and divide by n. So the matrix, what you have to do is that it's a kn matrix that you start with, WS, and you should get a k dimensional matrix after that. So what is left over is this index n. So you just you add up over that and then divide by n, which will exactly give you this quantity. Summing over the last dimension, keeping the k dimensional in. Okay, this is just a nice way of computing various things. The next one, what it says is that they have two matrices, WS, which is of dimension kn, XS, which is of dimension np, and then at the end you want a dimension kp value. So whatever is in the middle, which is n, which is not the right dimension over here, just sum it over that. So again, the new matrix mu will turn out to be the summation of Wji xi divided by summation of Wji over I. These are just fancy ways of computing these summations. Wji xi divided by Wjii. Now, the reason we do this, I could have written a for loop for doing this stuff very easily. Now, any idea why this is better than running a for loop? Why do I want to complicate my life by doing this as opposed to just writing a for loop? For those of you, have you guys used MATLAB? Yeah. So in MATLAB, one of the things that somebody must have told you is never use for loops. Why? Why don't you use for loops? So this is a little bit of how these languages are constructed. Python is not a compiled language. C is a compiled language. So when you write the for loop or whatever, you send it to the compiler optimizes everything. Python is a dynamically interpreted language. So every time you put a for loop, it will actually go step by step and do the whole calculation. If I call this function, this is a pre-compiled function. It knows exactly, it is already a compiled function. So when Python calls this function, it doesn't interpret it anymore. It runs way faster if you do it this way than if you do it through a for loop. Similarly with MATLAB, it's an interpreted language. So when you write a for loop, it goes very, very slowly. But on the other hand, if you do any kind of for loop construction using MATLAB's compiled function, it goes way faster. And that's why I'm going through this exercise of this, telling you about these Einstein sums, because when you do many of these EM type calculations, you have to do a bunch of these, and as a result it turns out to be that it's important that we figure out what happens here. Okay, what's going on over here? This is another Einstein sum. You have a matrix which is size kn, which is WS. You have a matrix which is of size k times n times p, which is this one, xs minus mu. There's a matrix of size k times n times q, which is this guy, and in the end you want a matrix of size k times p times q. The n, which is being repeated here, will be summed over. So at the end you will get a matrix of k times p times q, which is all the sigmas that you want. These are the mu's, which will be of size k times p, because there are k classes, there are p dimensional, each of them is p dimensional, so you end up getting that, and this is the matrix. Here's the, once you have computed all of this, you get the new log likelihood. If new absolute value of the difference between the new log likelihood and the old likelihood is less than the tolerance, you stop. Otherwise you set the old likelihood to be equal to the new likelihood and keep going, and when you break, you return the values of all of this. So that's what the story over here is. So now what have we done in this particular case? We had 3 classes, but then we decided that we are going to only train it for 2 classes. We can get what the numbers are. Let's get rid of this. I don't need it. And then here what I'm doing is I'm computing all the EM estimates, calling that function EM for generalized for Gaussian mixture model. This is EM for the Gaussian mixture model. You get that. Here all I'm doing is plotting the different points and making sure that I put contours around it. A lot of this is just counting, and then let's see, we run this. What happened here? Oh, I didn't tell you what that is. And then I don't even have this function run actually. Let's run that function. Hopefully, yep. And we run this guy, and then we run this guy. Whoops. What happened here? Oh, I had to define something over here. LL old equals, I don't know, 0. So now it has, what it's done is, question? Yes.
Varun, I have a very class 1 question.
Okay.
Nothing to do with this program.
Yeah.
For the past few months, generally I use MATLAB or old version of Fortran or somewhere C. Now in R I was reading that as it is an open source,
Yep.
there have been questions about the library functions.
Yep.
Shouldn't this type of questions are there for Python? Because I am not.
Oh, absolutely. In fact, much worse for Python.
Because I would feel more comfortable in writing my code in C or in MATLAB, which has already been tested, rather than use these programs where the likely functions, all these things are looks excellent. But if I don't get my result as per my what I
So I would say that for
this is a very general.
yeah, so for Python there are libraries that they maintain, which is SciPy, NumPy. These are very standardized libraries, and you don't have to worry about using any of those libraries. They're pretty safe. I mean, there's always going to be, even with C, there is no reason, maybe not the C systems, but if, for example, a lot of people who do numerical analysis use NAG routines. And you don't go about coding the NAG routine, because one of the ideas behind using these routines is that you want to build on top of those routines. You don't want to keep rewriting those routines. What is the guarantee that that routine is correct? The only guarantee really is that NAG doesn't want its reputation to be hurt, and there are so many users of that routine over and over again that the error will be detected. So if you're looking at SciPy and NumPy, which are sort of the basic numerical functions and the basic scientific function in Python, you're safe, because a lot of effort has gone into that, and a lot of people use those functions. If on the other hand you have downloaded somebody's GitHub project which has some libraries that you want to reuse or build over, then you have to be really worried about it. You have to make sure that those libraries are correct.
For R, I heard that's why this question.
In fact, for R, the situation is actually a little bit better than Python, because the reason is R libraries are typically coded by academics. Typically, not always, but many of them doing various kinds of machine learning algorithms are typically coded by academics. You would hope that they want to make sure that their old codes are correct, because their affiliation, their names and whatnot are there. With Python, the number of people contributing is much larger, and so the noise is much higher. But on the other hand, there is a culture of contributing and getting things, which means that what I would recommend is, instead of writing everything from scratch, if you get a Python function that looks like it's going to do what you want to do, walk through it to make sure that you understand what it's doing and correct it. It's often easier to walk through a code and correct it rather than to write the code from scratch. And so that would be my answer to this story.
What extra advantage will get using Python?
Sorry?
What extra advantage will get using Python rather than using R?
I personally prefer Python because the user base is much huge compared to R. It's a fully functioning language as opposed to R. R is a statistical language which manipulates statistics very well, but for example, it doesn't have object-oriented programming. Python is a fully object-oriented language. You can write just like you were writing all. So think about a following situation. Let's say that you are working in a company that has IoT devices connected to it. You want to grab some data from an IoT device, you want to do some data manipulation on it and send it back to the IoT device because it has some control functions that are available. You can write all of this in Python. You cannot do it in R. R doesn't have those low-level input-output languages. It doesn't have the control for all of that. But whereas all of these things could be done automatically, not automatically, but you can do it in one place. You want to define objects that are of interest to you, you can define them and use them. Whereas R is limited to statistical manipulation.
Also, there are some packages and option packages in R.
So R, if you're somebody who is, I used to code in R, but I switched to Python simply because I didn't want to do one kind of programming for normal programming and another kind of programming for doing data analysis. But there is, as I was responding to Raghu, our functions tend to be much better commented, much better produced as compared to Python. Now there is also R notebook, which makes the difference between Python and R that much lower. But at the same time, I really like the fact that Python is a language. It's like MATLAB versus C. If you write a Python program, you can compile it. You can call Python and compile it. whereas MATLAB is MATLAB. It's just sitting there. Okay, so if you did two classes from the data point that were generated, so those are clouds of data points. These are the contours that it found. It got one class sitting right in the center of that yellow circle and another class which is that dot over there. We can go back and ask it to generate three classes. And now the three classes it found are down here, the center of the yellow one and the green one over there. And let's see what the mu's it found so that we can compare what happens. Let's see what was the output, mu's. And what was the mu's that we put in. So these were the mu's that we put in, and those were the mu's that came. Do you think that this is reasonable? There's actually one big problem in this which we'll come to when I look at this data. So if you look at these two numbers, do you think that it's reasonable? First one was 0, 0. So that one it seemed to not have got. The 3, 3, what happened to the 3, 3 guy? Is it there somewhere in that data which is around 3, 3? The last one. The guy didn't know, the code didn't know that in which order I gave the classes. It doesn't know what class 0 is or class 1 is, class 2 is. It's going to find some permutation. So you can't expect it to exactly find 3, 3 in the second place because we just randomly started it. It found it there. It's about 2.85, 2.975. The corresponding to 0, 5, it has 0.006, 5.242. And it's got 0.215, 0.39, which should have been 0, 0, it's not there. So one problem with this Gaussian mixture model is this permutation problem. Sometimes things get permuted and you end up often cycling through several different permutations as you're converging. So that's something to keep in mind. The second one is, how do I decide what number of classes to take? So let me go back to 2. And then if I do the 2 and I get the mu, and this is what it found, this is what the true one is. Of course we can't expect the true one to be found, but it's found two mean values, which is what it's plotted over there. How do I decide which is the right one? What would be giving me the right numbers? Is there a way that I can figure out what is the right number of classes? Because nobody tells me what the classes are, right? All I know is that the data points. Somebody gives me the data points and says, okay, let's model these data points through a mixture of Gaussians. I would be very happy if somebody gives me that there were 3 classes, but if there were 3 classes, my problem is kind of solved. So the more troublesome case is when I don't know even the number of classes. So how would I do that?
Cross-validation.
What would I do in cross-validation?
So we just change the number of classes and just...
And then do what?
Plot the sum.
Plot what?
Mean square error.
Mean square error with respect to? Number of classes and what? Mean square error between the data points and the number of classes? No, that doesn't make sense.
The data.
Center of what?
The class.
Yes, but center of each class, and I compare it to what?
The data points in the class.
But remember, there are no data points in the class because each data point is probabilistically assigned to each class. There are no single no data point actually goes to a given class completely. It could come from that particular class with high probability, but we're not guaranteed. And if you look at let me go back to the 3 case because that will give you a little bit more sense. If you look at any of these data points, given that the standard deviation is reasonably large, if you look at that green, sort of not the first green but the second green one, the data points that fall in that second green sort of level set, they could have come from either distribution, right? So I can't say, hey, what is the mean, what are the points assigned to a class? What else can I do?
Weighted by the probability.
Yes, and then, but that's what I'm minimizing, right? So how do I know that 2 was right versus 3 was right? Good, weighted by the probabilities is a possibility. What else can I do? So I know as the number of classes goes up, what's going to happen to this mean square error? Can it go up? It will keep decreasing, right? So if I give you n is equal, if I give you 1000 classes, there were 1000 data points. If I give you 1000 classes, what will be the mean square error? 0. So if I say, oh, I'll keep on increasing the number of classes until my error doesn't decrease anymore, that's going to be a problem, because I'll keep on decreasing the error and it'll go to 0 at n equal to 1000, but clearly n equal to 1000 is useless. So how do I do this? We plot it, and then what are we looking for?
At that point, AR saturates. Means the AR is no more.
Perfect. So sharp changes. Great. So let's try to do that for our story here. So I'm going to define, I don't know, log likelihood. Instead of taking mean square error, I'm going to define a log likelihood. So I'm going to start with one class. That's the one class story. I'm going to define this as equal to LL. So that's the log likelihood that I got for one class. If I have a one class, that's the log likelihood that I'm getting. So minus 4329. Now let's go and make it two classes. Actually, maybe what I should do is I should take this thing and put it into the next one, because otherwise this is going to have to keep running two. And then let me look at what the log likelihood now is. That's that. So what happened to the log likelihood as I went from one class to two class? One class is down there, and the two class was minus 4267. So that was for one class. Now for two classes, let's run it for three. And I won't bore you for more than that. What did it end up doing? Yeah, 4260. 4260. 4 classes. So let's leave that over there. Let's plot the plot here. 4238. It still went reducing. And then you can keep on doing this for another one. And let's see what we end up getting there. So it looks like if you compare the two things, there was 4238 for 4 classes, 423837 for 5 classes. So it looks like around 4 classes it has converged. So we are not going to we would have discovered this to have 4 classes rather than 3 classes, and these would have been the classes that I would have generated out of it. So that would have been the answer that I would have calculated from here. So if you look at the mu's, that would have been the 4 mu's that you would have computed looking at the data. And anyway, you can run this story and figure out what further calculations can be done. All right. So what do I want you to take away from this? One of them I want you to take away is that Einstein Summation business. It's going to be very useful in various situations. Everything else is basically similarly the stories that we are developing. Zip is something that you use a lot of times. Enumerate, just make sure that I'm also having the extra indicator J, and that way I can calculate various things with it. All right. Returning back, I'm going to show you two more examples. One of them is a very practical one which actually came in a research paper. And then we will be done with this particular section. Okay. Next story that I want to talk about is imputing missing data. Here what we want to do is many times you take surveys and we want to be able to figure out from there whether the n respondents were asked to answer m questions. The observed data was x. VIQ was equal to 1 if I answered yes to a question q, 0 if I answered no to a question q, and nothing if I did not answer q. Right? So this is what the story is. YIQ are the indicator functions which is equal to 1 if the person I actually answered question q. Whether they answered yes or no, I don't really care, but they answered the question q. And it's equal to 0 otherwise. And what I want to do is I've run this survey. The respondent answered some questions, did not answer some questions. And now what I want to do is after I've run the survey, I want to be able to figure out what could have been their answers for the questions that did not answer. So the missing data is the questions for which they did not answer anything, and I want to be able to impute it. So how do I impute it? I'm going to assume, look, if every respondent is completely different, then there is no hope for me to fill in those questions that they did not answer. What I'm hoping is that when people answer these questions, they fall into different classes of people. And by pooling together, the answers come from a particular class, I can now try to figure out what they would have answered. Okay? So I'm assuming that there are j classes of people. Pi j is the probability that respondent belongs to class j. This is the same story, again a mixture model. Then you have class dependent probabilities of answering. If the class of customer I is equal to j, then the probability that VIQ is equal to 1, the probability that they would answer question I as a yes is sigma jq. It depends on the question and it depends on the class. It doesn't depend on the person. But there is still some randomness. It's not exactly 100% that they would have answered the question with a yes or a no. Okay? So the parameters that I'm after is pi and sigma. I want to know what are the probabilities of the different classes, and given the class, I want to be able to know what the distribution are. So the missing problem here is the class label of each of the person.
Sir, how we are estimating how many classes are there? J?
Same story as before. We will do cross validation or we will do some log likelihood analysis to figure out how many classes there are. Exactly the same story. So for now, we are going to assume that we know j and we calculate it, and then later on we'll optimize over j. So the missing data is CI, which is the class label for each person, and we want to know exactly how they fall into these different classes. Now I'm going to ask you, so the observed likelihood of the observed quantity is here. How did I write this down? X is the observed data, which is either 1 or 0 or nothing. So VIQ, I goes from 1 through n, Q goes from 1 through m. There are m questions, there are n respondents, that's the data. It could take value 0, 1 or nothing. So what have I done over here? I'm looking at the probability for each particular customer. I sum over the class probabilities, sum of j going from 1 through capital J pi j. If that customer belongs, or if that respondent belongs to class j, then if that respondent answers the question, that is YIQ equals 1, meaning that either they answered yes or no, then I know that the probability of that is going to be sigma kq to the power VIQ 1 minus sigma kq to the power 1 minus VIQ. This is simply binomial. So if they answered and they answered a yes, this part will come up. If they answered a no, that part will come up. Okay. There is no, this is not a k, correct that if you have notes, this should be j. sigma, because the class is j, so sigma jq, and 1 minus sigma jq. So this is the probability if they answered a yes, that is the probability if they answered a no. Okay, so here there is a blue question mark sitting. What is the assumption that am I making here? So what have I done in this particular calculation? I ignored these guys. I said that the questions that they did not answer has no information. The questions that they answered yes has information, the question that they answered no has information, but the question that did not answer has no information.
This is not a very big assumption to me.
You tell me.
Like, we designed the questionnaire
We designed the questionnaire.
because we place all the items that are having some relevance to our knowledge which we are trying to extract. And
Yes.
when I say that it did not answer this question, that means that does not contain any knowledge that I want.
No, but the person did not give you the information, so how do you get anything out of it? You decided to ask them a question, they decided not to answer.
Like in my case, it was I ignored, means I just rejected that entire response.
Yes.
Because he has not answered that question.
Yes, so how else so what is wrong with that? They did not answer, so I did not get that information.
For small data set we use.
Recommendation system.
What's that?
Recommendation system where the product feedback you wanted to analyze.
Yes, and they did not give me a feedback. So I ignored it. I don't have anything to do with it. So I showed them different products. That's a good example. I showed them where did it go? I showed them different products and I asked them whether they like it or dislike it. For some of them, they just kept quiet.
Yes.
I don't get any information from it, right?
Okay.
So therefore, I ignored it. Reasonable?
Yeah.
Okay. Now, on the other hand, suppose it's not product, but it's controversial social questions. Do you support the current Supreme Court thing that is happening about the Ram Mandir? Yes or no? And I ignored that question. Does that ignoring of that question have any significance for me? It does have significance on me. So if I look at the questions and I look at which questions these person actually ignored, there could be actually a pattern there and I could get some information out of it. But in the product recommendation case where there is nothing, I mean, by answering yes or no, I am not revealing some deeply held beliefs. This assumption is reasonable. But on the other hand, if you're doing any kind of political survey, this assumption is not reasonable. So you have to be careful about what model you're going to construct. So I just wanted to give you an example of a case where the model that you're going to construct in order to answer things, if you make this assumption for a political scenario, you are going to get answers which are not going to be reasonable. So you have to come up with some other better way of answering the question. You need to be able to figure out what is the information here. If they did not answer a question, what does it mean? You could turn around, and it might be an exercise, you can think about it and we can talk about it tomorrow or another day that I'm here. But this is not a trivial assumption. That's all I want to say right now. This is a fairly substantive assumption. In many cases where we are using data analysis right now in products, in services, in showing various kinds of ads, pretty reasonable. But on the other hand, the more social scientific surveys that people run, this is not a reasonable assumption. But once we've done it, I can march on. The class membership is unknown, so here's what I'm going to do. So I'm going to write the complete log likelihood. I'm going to figure out what is going to be the likelihood if I knew both the class membership as well as the answers. So there is the likelihood if Ci is equal to j, if I know that the ith customer belongs to the jth class, then the likelihood is going to be pi j times the product over yiq equals 1 of this quantity. If you expand it out, you end up getting one summation which just comes from pi j, another summation that involves sigma jq, another summation that involves 1 minus sigma jq. That log will bring the pi j down. Oh, by the way, I am using log and ln completely interchangeably. So don't make any difference between log and this log. Log and natural log are the same for me. Using the KL divergence trick for this pi, basically I take its coefficient, stick it up there and divide by the summation of everything. So it's just the coefficient corresponding to here and then divide by the entire summation. What happens over here? Again, I take this summation and put it up there. Oh, remove this log sigma jq. That is not part of the calculation. Remove this part and then divide it by the full summation. So VIQ, 1 minus VIQ cancels. So you just get the summation of these two terms. That is what is sitting down here. So that's a typo. That should not be there. So now I have this. Now if I want to do, just as a preview on the next slide that's going to come, if I want to do EM on this, what will I do? What will be, if I look at, let's say, sigma, oh, wrong thing to erase things with. Just to, we know, now that we know how to do a few of these EM calculations, let's take sigma star JQ. That is going to be the summation over I such that YIQ equals 1, that you answered the question. The indicator function, that CI equals J, VIQ divided by summation over I, YIQ equals 1, indicator function CI equals J. So how would I calculate this thing to be the next quantity? How would I convert this into an EM algorithm story? We will replace the indicator functions by expectations. What kind of an expectation? So in EM, this will be summation over I, YIQ equals 1. The expectation, of course, of the indicator CI equals J, conditioned on what information? The data that I have and the old set of parameters that I computed. And up here it will be the summation of the same thing, expectation of the indicator function CI equals J. Now VIQ is sitting there, conditioned on x and theta. Again, I such that VIQ equals 1. Okay. That's basically the calculation that's going to happen, and we will see in the next slide exactly the same thing. In EM, we will replace this quantity by that quantity. As an exercise, maybe you should run through the whole story. So there is one thing to say that this is what the answer is going to be. It's quite another thing to actually work from first principles and show indeed that is what is going to happen. So in order to do that, what you want to do is take the expectation of that complete log likelihood function and then compute what the corresponding values of pi and sigma will be and show that they are exactly the same. So that will be the calculation that you should do offline to make sure that you understand what's going on. And here's what the entire story is, but you can check to see that this is indeed what is going to be correct. So you've got the probability of yi equals j given vi and theta k. Actually that is yeah, so here in this line correct this to be ci, the class label. Ci equals j, not vi. I will correct these and upload and put it onto the shared file so you can upload the correct ones. And after that you just calculate the various things and you'll end up getting that the Q function is that. From there, if you do the log likelihood, you'll end up getting the right answer. So those are the right answers. I won't go through it because it's basically an exercise of the same kind, but I'll encourage you to look through it to make sure that you understand exactly what is going on. If you look at this expression, the reds and the blues, and you compare them to that expression, the reds and the blues, you will see exactly the parallel that is coming. All right? Good. All right. So then I have one last example before we switch to SVMs, which we'll do after the break. Now I want to do is a topic which is this example is going to be a little complicated. I want to give you a background of this problem a little bit, and then I will try to explain to you what's going on. So there's an important, very important topic right now, which is called assortment optimization. What is assortment optimization? It's motivated by online, sort of online products and online commerce, e-commerce. So when you go to Amazon, let's say, just to pick, or Flipkart, now that I'm in India, although I see today that there was some major shake-up in Flipkart. So let's say if you go to the Flipkart website, they know something about you because you have an account with them. You've purchased something from them before. And what they want to show you is what set of products should I show you when you search something. I have lots and lots of products. I have to be able to decide which subset of these products should I show you. What does this thing depend on? It depends on what you like. Maybe you're somebody who really loves to have top of the line products. Could be somebody who likes many features. Somebody who doesn't care about color as long as the features are good. All of these factors that depend on the person goes into this decision. But there's also another component, which is how much inventory I have. Now, it may be that I know the perfect product that you like, but I won't show you the product because there's a possibility somebody else will come along later who will buy just that product. Whereas you are not so choosy. You might buy this product or that product. So I might be able to get your business as well as the second person's business if I don't show you this product and reserve the product for later. So this question of what products to show is very important. And to some extent, the last the question that we were looking at before, which is about whether you like it or not, that will be done something before analyzing what are the products that to show you. So this particular example that I've taken is from a paper that appeared maybe 5 years ago, and they were and they actually used EM to learn various preferences of people based on the data that they collected about them, right? So, and this is the story that what happened. So there are capital T time periods. There are a set script P of products that are available. So there are little p different products, and typically 0 is a no purchase. So basically what happens is the way you model these things, a customer comes in, they look at the set of products that you've given them, but at the back of their mind they have another product, which is they don't like any of them, and they walk away. Or they have an alternative somewhere else which is better than what you have offered. So that's what I'll call no purchase option or the 0 product, right? At time t, we are going to display a set ST of products. I'm always going to assume that the product 0 is part of ST. If you don't like this modeling, then just define script P to be 1 through P. Make sure that you pick a subset ST of products from 1 through P and add the 0 product to it. Either way. So either you assume 0 is always part of that set, or there's other ways of looking at it. Lambda is the probability that a customer arrives in period t. Think about these periods to be in seconds or microseconds, whatever depends on the traffic that you're talking about. And in each unit, you have a certain probability that a customer arrives. Question? Question? Or good? Okay, perfect. Okay, now let's parse through this model. Here's my customer arrival model. I'll walk you through this a little bit slowly because there are a few different things going on. Again, I have m classes of customers. How do I figure out how many classes? This is again a question of cross-validation and figuring it out. Xi's are the probability of class I. That is, a particular customer belongs to class I with probability Xi. A class I customer is described by a permutation on products 0 through P, right? And the way this permutation helps describe their preferences is follows. If in this permutation, sigma, you're looking at the ith class of customer, if sigma I of j is less than sigma, this should have been I as well, sigma I of k, then this particular customer prefers j to k. Let's go down here. Take the particular permutations of products to be 2, 1, 16, 0.
So what actually actually they're comparing? Describes.
This means that I like product J compared to product K. Doesn't matter, I pick it. If you give me J and K, I'll pick J. That's it.
Actually comparing what? Means product J is greater than product K. What is greater than what?
I'm more likely to buy it.
Okay.
That's all I care
So
about.
how will you capture that? Which I am more likely to buy?
Because I have the buying data about the customer. So from that I know what they bought. Question back there somewhere? Yes.
The second point, the permutation of
Yeah.
0 to B.
Yeah.
I'm not able to understand it.
Okay, so let's write this down. So let's say I have 5 products and my product set is 0, 1, 2, 3, 4, 5, and I have a permutation of these which is 5, 1, 3, 0, 2, what did I miss? 4. So suppose this is a permutation of these 5 products. So what this permutation means is that for this particular customer, 5 is preferred to 1, is preferred to 3, is preferred to 0. So if you show them these products, if you give them a, suppose I showed them the product 1, 2, 3, 4. Suppose this is the set of products that I showed them. And let's say 0, 1, 2. This is the set of products ST that I've showed this customer. So if their preference list is this one, which product are they going to pick? 5 is not shown. 1. So I'll go down this list and see which product is here. I'll check 5, not there. 1, yes, I'm done. So if you show them this set of products, this particular customer is going to buy product 1. What if I gave them the set what happens in this case? 0. What does 0 mean? No purchase. So in this particular case they will just walk away. They will not purchase anything. So that's what I mean by this permutation. So this basically is a notation. If J, this should have been an I, not a J. What it basically says that if J comes before K in the permutation, then I prefer that over the other one. So I prefer J over product K if J comes before K in the permutation. That's what that definition is. The customer picks the highest ranked product. Remember, 0 is always part of it. 0 is always part of the product set. And so after 0 I don't really care. Even though there could be millions of products, as soon as I find a 0 in my permutation, after that I don't really care. Because after that I will not purchase anything. Right? So that up to 0 I need to care. Yes?
So how will you interpret the sigma method?
This one? This?
You have put that 0 as no purchase in between.
Yes.
So what will the interpretation of 2 and 4?
Nothing. It's just easier for me to think about permutations rather than to have these permutations which don't have unequal lengths. So in order to not worry about this unequal length of permutations, I just allow for everything. Because if this 0 had come over here, for example, I missed some number. Suppose the 0 would have come here, then only 5 0 matters. And then I have to keep track of how much was the length of the permutation and so on. So instead of that, I just put the permutations. But implicitly, I know that as soon as I get a 0, after that it doesn't matter. Because 0 is always part of every set. So no matter which set I give you, the moment you prefer the no purchase option, you're gone.
So we select permutation according to class.
Yes.
Class of a customer.
Yes. So we're going to say that all of you are going to be described by some permutation. And the total number of permutations is a lot smaller than total number of people. I mean, total number of permutations is actually a large number, but the number of classes is smaller than the total number of customers. And every customer in a particular class uses the same distribution, right? Okay. Now, what we want to do is figure out how to, the data that I have is the following. I showed a set of products at each of these times. Capital 1 through time little t1, little t to capital T. I showed them different products. That was the set of products that was shown. This was the product that was selected by a customer arriving at time t. I don't know what class this customer belonged to, but he came and they purchased this product. Now we want to figure out what was the class of this customer, what is the rate at which people are coming. So what are the two things that I'm after? I want this probability xi and I want lambda. These are the two things that I'm after. I'm going to assume that this I have pre-computed. I know that for each class what do they like. How do I know this? Because I've done some surveys on people before. I've shown them some products. I know what they like. I just don't know that a customer coming in, what particular class they belong to and how fast they're coming. So that's what I'm going to try to estimate. Question? Yes.
What happened, for example, with this particular example, if a customer comes and the traffic intensity is not that high,
Yeah.
so he couldn't wait to see even a product, calculus of him choosing or not choosing anyone.
Yes. So what you're saying is that lambda might be very small. That's fine. So what you're saying is that let me give you a preview. I am going to allow for the possibility that there are periods with no arrivals at all. So there is a probability with which people arrive. There's a probability with people do not arrive at all, and so I need to make sure that I take care of that possibility when I'm estimating lambda. Is that your question?
No, not particularly.
Okay.
What I'm saying, let's assume the customer came and is in the queue.
Yeah. But they're not a queue. So to think of this model as being on a website.
Okay.
So the customer sees the product immediately. They are not in a queue. So, and then if the customer arrives, they see a set of products and either they pick something from it or they walk away. That's the data that I have.
Waiting line model.
So it's not a waiting line model. It's not like, because it's not the case where you stood in line and by the time you showed up, that's actually also a very interesting problem, because what if there was censoring? You didn't see the product because the inventory ran out. That's, in fact, with a student, we have a paper on that problem which is recently happening, where how do I save inventory for future customers? Because if I save inventory, it means that I'm losing revenue. But then I might be able to sell that later for somebody who really wants that product and may be willing to pay a lot more money compared to somebody right now who I just give it away at a lower price. So we have to worry about it. In this particular model, we are not considering it. Here we are basically saying customer comes, I show them the product, they purchase something or they leave. Okay? All right. Now, where did we go? Okay. Let's try to mathematize this. Okay, that's good. We have about 10 minutes. We should be done with that. So the mathematization of this story that we are going to do is the following. Given the set ST and given the purchase JT, I want to look at all possible classes of customers that would have picked JT from the set ST. So what am I saying here? I'm looking at all possible classes I, for which the sigma corresponding to that particular class will put product JT before K for all possible K in the set ST. And this is an inequality, therefore JT will also be okay here. For all possible products that I have shown, this one is the best. JT is the best. Find me all such classes, call that the particular, this is the set of all classes that could have purchased the product JT from ST. If a class does not belong to this set, then they would not have been the class of this person, because they would not have purchased JT from the set ST. So what is the probability given the set ST that you pick the product JT? That is basically the summation of I belonging to this set M of xi's. All possible probabilities of classes that belong to this set M is the probability that JT will be picked when the set ST was shown. All right? Okay, good. Now I want to write the log likelihood. A is the periods in which there was an arrival. A bar were the periods in which there was no arrival. For all time periods that there was no arrival, the log likelihood is just log 1 minus lambda. This is the probability of not seeing an arrival. Lambda is the probability of seeing an arrival. 1 minus lambda is the probability of not seeing an arrival. These are all the time periods in which there was an arrival. So what is the probability of seeing product JT, ST? It's the probability that somebody showed up, that's lambda, log lambda, plus log of the probability of JT given ST, and here's the quantity over here. You sum them up, it's the number of periods in which there was an arrival times log lambda, that's the term from here. Number of periods where there was no arrival, A bar, times log 1 minus lambda, that's from there. The optimization on lambda is pretty clear. I just look at these quantities, and what is lambda here? Now that we have done is multiple times. What is the value of optimal value of lambda? It's just the size of A divided by the total number of time periods. That's going to be the lambda, which is pretty reasonable. That goes away. This guy, we are back in our story. I have a log, but I have a summation inside. So we want to treat this as a latent variable estimation problem. Again, what is latent? Latent is exactly the class. I don't know which of these classes, which particular class out of this set of classes did we arrive. So I create a complete data set. IT is the class of the arriving customer, JT is the product they produce, pick, ST is the product that was offered. Now if you look at the complete log likelihood, you end up getting that this term is as before, this one. Now for all I belonging to the set, if IT is equal to I, log xi. Why am I taking only the summation belonging to these ones? Because for all the other ones, this indicator function has to be 0. It could not have been one of those classes. In fact, I could take this and forget about this and just incorporate it right there, and still life would be fine. You can optimize lambda directly without using EM as we did before. The cube function for estimating x is given the data, given the x case, what is the conditional probability that a class of the customer arriving at time t is equal to I log xi. Now we need an expression for this quantity. This is the probability of this conditional probability. We'll do the same trick. I don't know the conditional probability, so I'll go to the joint. I will write it differently. Given x case, what is the probability that the class is I? Given that the class is I, what is the probability I saw the data? That is basically, this one is xki, and this one is just the probability of seeing product JT given ST and I. That one is simply the indicator function that I belongs to that set. So xki, I belongs to this set, call that MIT. That's a number that I know, and therefore that expected value now is simply these MITs divided by all the summations. If rho IT is equal to 0, then we know that I could not be in that set, and I'm fine. It's not going to bother me. As I said before, it's not something that it's going to kill me. So now I have this x star is the argmax of this quantity, which is a summation of rho IT log xi. Again, we have the same log trick. We know that the optimum value of x star is take all the summation of rho i's that correspond to a particular t over the entire summation, and that's it. That's basically the end of what this calculation. In fact, if you're interested, I will update the slides and put down the reference of this paper. It's a nice paper. It appeared just about 4 or 5 years ago. So we are coming to a point where if you knew how to solve this and you had data from some company, you could actually have a published paper. But unfortunately, somebody did it already, so you can't publish it today. But 5 years ago, you could have. But there is a lot of interesting things that are going on in the EM space, which is worth looking and seeing. And in fact, in the next, not on support vector machines, but the next story that we are going to see, which is on matrix decomposition, we will see EM again. And in order to build up towards that step, what I want to do is, I want to show you that there is expectation maximization is a variation on something called a minorization trick. And we will see this minorization trick again. But here's the basic idea. Suppose I have an optimization problem, which is so I'll show you this, and then when we come back, we'll be in time for a break, but when we come back, I'll show you how this is connected to EM. So suppose you have a hard optimization problem that you want to solve. You want to maximize some function f of x such that x belongs to some set capital X. And let's say that this is a hard problem. What you do is you create a function g of xy of 2 variables such that gxy is less than equal to f of x for all values of y. It's no matter which value of y you pick, gxy is always less than equal to f of x. But if you set y equal to x, then gxx is equal to fx. Oh, okay. And let's suppose that if I fix the value of y, this maximization is an easy problem. Okay, this maximization over x for gxy is easy. And I won't have the time right now, but when we come back from the break, I'll show you how this connects to EM in a moment. Now let's define an iterative algorithm, which does the following. You start from any value x, x0, you optimize this, call that x1, put x1 here, optimize this again, call that x2, put it here, x3, and so on. Keep going. So what will this do? So let's think about it this way. So let's look at the function fxk, the function at the kth iterate. By this property, I know that gxk, xk is equal to fxk. Then what I do is I don't take this value of x, but I maximize over that. So I know that this quantity is larger than that quantity. Why? Because I can always choose x equal to xk, in which case I get back this, but I'm maximizing, so this is going to give me something larger than that. Great. Let's call this maximization according to this gxk plus 1 xk. What happened over here? I use this property. For any value of y, gxy is less than fxk. So gxk plus 1 xk is less than equal to fxk plus 1. So now I have, if I forget about everything in the middle, I know that if I look at the iterates, their function value is increasing. Will it going to converge to the optimal? Maybe not, but at least it's going to improve. And if you think about it for a moment, and I don't have time now, but and by this time I think you guys are also need some coffee to wake up. I'm going to go all the way back and show you this beginning of this story of EM, and that's right here. And if you want to play around with this, look, here's a function that depends only on theta, L theta. This x is just sitting there nominally. This is a function of theta that I want to maximize. Now I have a function of two variables, q and theta. Now I have this nice property that no matter which value of q I pick, LQ theta is below L theta. Script LQ theta is a lower bound on L theta. So we are setting ourselves into the format that I was talking about. This is your f of x, this is your g of qx. No matter which q I pick, it's going to be, this will going to give me a lower bound. The thing that I don't yet know is to show you that there is a value for q for which this is an equality. And think about it, and then after the break we will work through this a little bit, because this will show up again later on in these lecture series. Alright, we'll take a break now.